Welcome to the video for Polar Calculus Day 1. Today we're going to explore polar calculus, or more so just polar coordinate systems, which is another way to locate a point on a plane. We have typically dealt with a XY plane where we were told we went out 3 units in the X direction and up 4 units in the Y direction, and that's where we had a point. And that is usually referred to as the Cartesian plane or rectangular coordinates. And what we're going to learn about is polar coordinates, which is just another way of representing a point on a plane. Okay, so for polar coordinate systems, there's 2 pieces of data. Just like with rectangular, we had the X coordinate and then the Y coordinate. And the X would tell us how far left or right to go, and the Y coordinate would tell us how far up or down to go. In polar calculus, we have 2 coordinates, and these coordinates are r and theta, or 2 pieces of the coordinate. And r tells us the radius, and theta tells us the angle. So what we're going to say is, on this drawing here, we have plotted the point 4, pi fourths. So what that means is, from our origin, we're going to go out 4 units, and that would be this entire circle is out 4 units. And then we want to locate the point that is pi fourths of a radian. So if this was 0 radians, pi fourths radians is located here. And we go out 1, 2, 3, 4 units. And that's where we hit the location of our coordinate. So that's a polar coordinate. Radius, then the angle theta. So find several other equivalent polar coordinates. So we've already established that our polar coordinate, r theta, is equal to 4, pi fourths. But there are several other possible ways we could refer to that point. Perhaps we go out 4 units and then we rotate pi fourths plus a whole nother circle. So we also have 4, 9 pi fourths. That's a alternative coordinate for the exact same location, because we have 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, 8/4, 9/4. So 4 units out, 9 pi fourths around is right there. We could keep going. We could go several circles around. We could go another 2 circles from that point, and we'd arrive at 17 pi fourths. So there's some equivalent points. We could also go backwards if we wanted to, say, go to the point 4, but we're going to back up 7 pi fourths radians. So that starts here, and we back up 1, 2, 3, 4, 5, 6, 7 pi fourths, and we get that angle there. Close that bracket, or parenthesis. Another thing that we can do is we can have negative radiuses. So if I plugged in -4 and 5 pi fourths, what that's going to do is take my angle and go 1, 2, 3, 4, 5 pi fourths. So we're out at 5 pi fourths, and instead of going out 4 units, we're going to go backwards 4 units, and we'll get to that point as well. Along a similar vein, we could also have the 2 circles later of 4 and 13 pi fourths. I guess that's 1 circle later. So counting that out, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 pi fourths. And then we're going to back up 4 units. There we go. And this list could go on and on. We can just keep throwing down possible coordinates, -4 and -3 pi fourths. these are all the exact same point. And that point can be represented either in the polar form or as a Cartesian rectangular coordinate, the xy coordinate. And the way to find your xy coordinates given a polar form is we can go back to looking at how our unit circle works or some trigonometry, and we see that x is the equivalent of r times cosine theta, and y is r times sine of theta. And this is going to be a key which is very important to memorize to be successful in polar calculus, because we'll be doing this coordinate change several times. So polar right there, we want to convert these to a polar coordinate, from a polar coordinate to a rectangular coordinate. So the x value is the radius times cosine of our angle, and that gives you an x coordinate of 2 root 2. And then we can do the same thing for the y coordinate. Y is equal to radius times sine of pi fourths, and we get y is also equal to 2 root 2. So in rectangular coordinates, we are located 2 root 2 comma 2 root 2. And looking at our graph, that seems about fair. We've gone out a little over, looks like a little over 3-ish units, and we went up the same amount. So that distance was 2 root 2 and 2 root 2. Alright, so the key conversion that we need to memorize is right here. We'll learn about how to convert back from rectangular to polar and polar to rectangular as we move forward. Alright, at the bottom of the page it asks us why use polar coordinates. Well, sometimes graphs that aren't functions in rectangular coordinates, for example the circle here, it's not a function as a rectangular coordinate system, but if we express it in a polar form, it becomes A, easier to look at, and B, probably easier to do calculus on. And we are going to see some pretty elaborate, beautiful curves that are much more easily expressed in polar rather than rectangular equations. So before we get to drawing our own polar curves or seeing some of these elaborate curves, let's draw some really basic polar curves. Alright, to the next page. Okay, the first one, we want to sketch the curve radius equals 7. And so what that means is we want to plot all the points that are 7 units away from the origin. So 1, 2, 3, 4, 5, 6, 7. That's going to be this circle right here. And pardon the imperfection of my stylus, but 7 units out, just a circle. That's a very simple equation, circle. The second one, we want to capture the circle between 1 and 2. So that's going to be this circle and that circle. Those are radius 1 and 2. And we're interested in only the area between pi and 3 pi halves. So this is pi, and this is 3 pi halves. So the area of interest is just this little chunk right here. Kind of hard to draw with the stylus, but I think you get the idea. Going to the third one, we want the circle between 2 and 3. So we go out 2 units, 1, 2. That's this circle, and 3 units. That's that circle. Again, poor stylus work. And from pi 6 to 5 pi 6. So pi 6 is that angle, and 5 pi 6 is that angle. And maybe if I zoomed in, it would be easier to do. Okay, pi 6 between 2 and 3. So all of this. And technically, if I'm trying to be perfect here, I should have a solid line at the radius of 2 and a dashed line at 3. But we're overlooking that fact because I can't draw well with a stylus. Okay, going to the next one. We want the region where the radius is less than 3, so that's going to be 1 unit, 2 units, 3 units. So we're going to be drawing a circle of radius 3, and we're dashing it because it does not include 3, and we want all of that region less than, so we're getting the area trapped inside that circle. And finally, next one, between 1 and 3, we don't include the 1, so we're going to dash a line at 1, and we're going to include 3, so we do a solid at 3, and it's between pi halves, that's this angle here, and 9 pi fourths. We got 1, 2, 3, 4, 5, 6, 7, 8, 9 pi fourths. All right, so there we go. Let's color in the region between 2 and 3. Right, like that. So again, solid on the outside, dashed on the inside. For our class, we probably won't be doing too much of these graphs. I just want you to get familiar with kind of the idea of the radius measurement and then the theta measurement, the angles. Okay, the rest of these we're going to rely on our graphing calculator to help us draw them. Example 3, we have some equations here, and it says put your graphing calculator in polar mode and radian mode. So all of our calculus should always be functioning in radian mode, and then this polar mode, that's the same area where we went and we looked at, we had function mode, we had parametric mode, and now we have polar mode, and we're going to be operating in polar mode. And when you go to the y equals button, instead of it saying y equals, it will say r equals. So if we press y equals, we can type in our equation. And the rest of this section, I'm going to let you explore what drawing in examples 3, 4, 5, and 6 look like. And after you draw them, I want you to answer the questions that are associated with these drawings. What do you notice about the curves? And try to write down as many things as you notice. In class, I'm going to review and talk about what are some important things that you should be noticing when learning these. Ultimately, we have a series of equations that we're going to need to start to have a pretty good memorization for what the curve looks like so that we can sketch these things quickly. And all through the polar calculus unit, we're going to be drawing these curves, so we might just pick it up naturally after we've done it several times. But for now, use your calculator, sketch each one of the examples very quickly on the grid, and then write down all the things that you notice about that curve. Okay, hopefully you've learned a little bit about polar graphing, and you've learned that equations of the form a sine theta or a cosine theta draw out as circles on the polar grid, and then maybe you'll learn something about the equations a plus b sine theta or a plus b cosine theta. And those are going to, depending on the values of a, trace out as a cardioid or a limison, or maybe a dimpled limison. All right, we'll talk more about it in class. Thanks for watching.